Well, hello, class. I am doing another lecture, which is a continuation from our earlier lecture. It's just that it's much later in the day, and I've been planning to do it for a while, but then I did a whole bunch of other things that really were meaningless. But that's the point. You do things when you can, and so here I am. And what I wanted to do is I wanted to continue looking at that RC circuit and see why that RC circuit creates that voltage profile that I showed you in the last lecture. So this is really just a continuation of the frequency response lecture that we had earlier. And let me redraw that circuit. We had an AC circuit that was going through a resistor and then was going through a capacitor. Now, I want to remind you, let's go back to DC, right? When we had a DC circuit here and we had a resistor and we had a capacitor, what happened? If you remember, the DC source fed into the capacitor like it was a bucket. In fact, it sort of fed into it like it was not a bucket, but a bottle where water was coming in, and it was like a pressure chamber. Water comes in, and what's it doing to the air that's already in there? It keeps compressing the air and compressing the air until it slows down. So what we saw was that over a period of time, when we were looking at the charge discharge, we saw that if this was voltage and this was time, that the thing would charge up over a period of time. And then if at that time, let's say T1, it started to discharge, it would then discharge over a period of time too, wouldn't it? Right? That's what a capacitor does. Also, I want to say another thing about a capacitor for DC. It starts like, when you first throw the switch in a circuit where this RC circuit was a DC circuit, what would you find as far as the current goes? Well, it starts in DC, and again, let me point this out here. This is DC. I'm going to make a little box here for DC, right? For DC, what we find is that it starts as a short circuit, right? And then it eventually goes to an open circuit. So in the beginning, current flows out of this as if the capacitor wasn't even there. Now, I'm not talking about an AC circuit, I'm talking about a DC circuit. I'll draw the DC circuit right over here. In fact, why don't I put it in here so that you'll have it in your notes. If I have a DC circuit and it's a resistor and a capacitor, what it does is it starts out as a short circuit. That means that the current is just flowing right through that as if the capacitor wasn't even there. And it's flowing through there at a rate that's what? It's flowing through there at a rate that's V over R. The voltage, whatever the voltage is over R, right? Now, let's look at this circuit, though, and this is the circuit that I'm looking at because we are talking about frequency response, aren't we? So what we want to do is we want to find out how this would change with frequency. And in my other things, I had, I wonder if I can turn this whole thing. No, I don't know if I can. In the last lecture that I gave, I said that the resistance would be like 5,000 ohms. And then C, I said, was going to be, I think it was 1 microfarad, right? And we found a couple things out at a variety of different frequencies. We found out that at a very, very low frequency, at 10 hertz, if we wanted to look at just the impedance of both the resistor, I'll just put the resistor impedance here and then the capacitor impedance here, right? So at 10 hertz, well, we still have the 5,000 ohms, don't we? But over here, we have 15,915 ohms. And of course, this would be at 0 degrees, but this would be at minus 90 degrees, right? Now that was at 10 hertz. If we went up to 1,000 hertz, actually, before we get to 1,000 hertz, let's go to our magic frequency. Our magic frequency was our cutoff frequency, which was 318.3 hertz. And so at 318.3 hertz, we have 5,000 ohms for our resistor and 5,000 ohms for our capacitor, right? Of course, this still being at minus 90 degrees and this still being at 0 degrees. I'll just put a 0 in there. Right, so that was where we were even. And then if we went up to, well, I'll do both of them, 1,000 hertz. We found out that, of course, we still have the 5,000 ohms at 0 degrees here, but we ended up having 159 ohms here, right? At minus 90 degrees. And then when we went to 1 megahertz, it was even much, much, much higher. So what you can see is what predominates here is Z sub R. And what predominates here is Z sub C, and here they're equal. I'll just put equal so that I can cross out that ugly black thing that I now have. Oh, what do you know? I happen to have whiteout. There we go. Now you can't even tell that I made a mistake there. So right here, they're equal at the resonance frequency, right? At that resonance frequency, they're going to be equal. There's a couple things about the resonant frequency, and that's what I'm going to talk a lot about. But first, I want to talk conceptually about what is going on in this RC circuit. Now, you know that this is grounded down here, so our voltage down here is 0 volts, right? Now, what's our voltage at A? And how do I find out what that voltage at A is? And that's what we're going to look at. And I think that I said that this was 100 volts peak. So we'll look at how the voltage changes at A. Now, I already told you how the voltage changes at A, and so I want to write that down. Because if we're looking at a graph of the voltage at A with frequency, now it's not time, is it? This is not a waveform I'm showing you. I'm showing you the voltage at A versus frequency. That's what I'm showing. And here's what it looks like. And this would start off with 10 volt, with 100 volts, right? So it would start off with 100 volts, and it would look like this. Right? So the voltage at A would start very close to the 100 volts, and then it would drop off very quickly as we go further and further and further away. And there's a special. Now, what is that special frequency, that cutoff frequency that I'm talking about? What's that value going to be? So my cutoff frequency is going to be V of A equals 70.71. There, we see it all over again, don't we? 1 over the square root of 2, just coming back and constantly talking to us. Volts. That's what it is. So that's going to be the voltage at A. Now, I'm not telling you what the phase angle is, but we figured that out the last time that we were here, and that was going to be minus 45 degrees, wasn't it? So that was in our last lesson. And so we know what that voltage is. Now, that voltage is very special, by the way. I I don't know if I want to get off track here right now, but this voltage with a 70.71, of course, you know that that's 1 over the square root of 2 times the source voltage, which is 100 volts peak, right? So this is still volts peak that I'm talking about here. It's not RMS. Although the RMS value for 100 volts peak would be 70.7 volts, wouldn't it? But this is 70.7 volts peak, and that's what's happened because there's been a voltage drop across the resistor. And that's why it's now 70.71, and it's at a minus 45-degree angle. But let's look at the actual mathematics of what we have here. Now, if, for instance, we look at this at a very low frequency, and where would the very low frequency be? It'd be right about there, wouldn't it? So if I'm looking at this at the very low frequency, I would think that V of A is going to be very large. Well, how does that happen then? If we look at this very low volt frequency that we have here, 10 hertz, we see that's 5,000 and that's 15,915. Well, let's add these two things together to get the total. So at 10 hertz, what is our impedance going to be? Well, our impedance, our total impedance for the circuit is going to be my 5,000 ohm resistor, right? Minus 15,915 ohms, right? Oh, I forgot J, sorry. So 5,000, it's a complex number. So that's my total impedance at 10. If I wanted to write that total impedance as a vector instead, that would be 16.69 kiloohms at an angle. Wait, don't tell me. I'm gonna have to figure it out here myself. Just a second. 15,915 divided by 5,000, and that quantity taken to the inverse tangent gives me minus 72.56 degrees. Okay, so 16.69. Now that's a huge number, isn't it? You know, if we then wanted to find out what our current was going to be, and again, I want to circle this too, because that's the important thing. We're doing this. This is our first one we're going to look at. It's at 10 hertz and see, well, what kind of current is going to be involved in this? Well, we've got 100 volts, right, peak. So we're talking about peak current. That's what we're going to get out of here. And that's at 0 degrees. And then we want to divide that by 16,690 ohms at minus 72.56 degrees, right? Am I still on the page? Yes, I am, but I'm getting down there to the bottom of it. Okay, so obviously that gives us I, doesn't it? So I've got, well, actually, I didn't even do that. 100 divided by 16,690 gives me 5.99. Let's call it 6.0, and I'm going to put a line over the O to show that that's a significant figure. In fact, I'll put another one there, put a line over both of them to show that they're both, because it's 5.99. So 6.0. Milliamps peak at an angle 0 minus 72, so that makes it a plus 72.56, doesn't it? Okay, and so that's a very, very small current, that we're looking at here. Let's just encircle, well, I don't want to fully encircle this yet, because we want to look at that voltage drop, right? Well, if we've got this and it's a plus 72, then what's my voltage drop across that resistor. Isn't it the current, which would be 6 milliamps peak at 72.56 degrees? I'm going to multiply that because it's I times Z, right? So Z is just going to be 5,000 ohms at 0 degrees. So the voltage drop that I get across that first resistor, and of course that's going to tell us what the voltage is at A, because if I take 100 volts and I subtract the voltage drop I have across the resistor, then I'm going to find out what the voltage is at A. So let's just do that. And I find out that I have approximately a 30 volt drop. And what's the angle that's going to be that's the 30 volt drop? It's going to be 72.56 degrees, right? If we wanted to, we could then break that 30 volt drop down into its two components because we're going to have to subtract it from 100, aren't we? So if I have 30 times the cosine of 70, wait a second, the cosine of 72.9 times 30 volts gives me 8.97 volts plus J, and then it's just going to be 30 times the sine, and that equals 28.63, 28.63 volts. So there you go. So that's my voltage drop across there, and that means that the voltage at A is going to be in, and this is what's going to surprise you. This is why I wanted to do it this way. I really wanted to, I like to teach people like they're engineers, not like they're technicians. This is the math that separates us, isn't it? And so let's look at the voltage at 8 now. And you're probably thinking, well, okay, 100 plus J0. Well, this is going to be like, well, let's see, 8.97. That's about 9. And this is about 28. So 9 and 28, well, that makes about 37. Oh, my God, 100 minus 37 is 63 volts. What do you know? That's not what it is. Of course, that's not how it works at all, is it? It's rectilinear coordinate. Anyway, let me just show you. So 100 plus J0 minus 8.97 volts plus J. Now, of course, that plus is going all the way through there, 28.63 volts, right? So 100 minus 8.97. 100 minus 8.97 gives me 91.03. And you're saying, okay, well, hey, don't forget that 28.63 volts you've got there. That's right. So that would be minus, because I've got 0 minus a positive, so that gives me minus J 28.63 volts, right? In fact, I should put parentheses around there because I didn't put volts there. So what is the voltage at A? Let's just look at that for a second. Now, what am I doing? I'm just squaring those and taking the square root, and I get 95.43 volts. 95. It didn't make it less. It made it more. Don't you see how? But what's the angle now? Right? The angle, if you look at it, is no longer going to be a positive angle, is it? It's going to be a negative phase shift angle, because now I've got the minus 26. So let me give you that angle. So 28.6 divided by 91.03, and then take that quotient and find the inverse tangent of that, and that gives me 17.44 degrees, and that's minus, isn't it? You remember, your calculator is going to screw with you because it doesn't know if it's in the, it thinks it's in the first quadrant when in fact it's not. It's really in the fourth quadrant. So it's minus 17 point. And look at that. We haven't really lost any voltage, have we? Right? We haven't really lost any voltage going across there. And that's right, because if I follow this up, what would I expect at that point? I would expect to have something very close to the voltage that was put in, 100 volts, and I've got 95.43 volts. What if we go at the other end? Instead of being at 10 hertz, let's go up here to 1,000 hertz, right? So I hope everybody can see this, at 1,000 hertz. Okay, well, at 1,000 hertz, my total is going to be entirely different. My total impedance, you can see it's 5,000 ohms, right? Plus J159. I'll just say 159 ohms. And that's it. And so if I wanted to write the total impedance there as a phasor rather than the complex number rectilinear form, A plus JB, it would be 5,000 squared plus 159 squared taken to the square root, and that gives me 3,020. Oh, wait, what did I do wrong here? Excuse me. Yeah, whoa. Hey, get the, sorry about that. Obviously, I left something in the calculator or whatever. Yeah, because that is supposed to be around 5,000, right? 5,000 squared plus 159 squared taken to the square root gives me 5,002. That's better. 5,002 ohms and an angle that's got to be very close to 0, doesn't it? Right? 159 divided by 5,000, and then take the inverse tangent of that. That gives me 1.8 degrees. So very close to, well, you know, to write straight on real numbers. I should write the complex plane here to remind you how it works. There's my real, there's my imaginary, there's my complex plane. Now, let's take that a step further, just like we did before. What is I going to be then? Because remember what we got down here as far as I was very small. I wanted to circle this at the time, and the reason I didn't was because we were, you know, in the midst. But I want to point out I to you. And I also want to finish this little rectangle down here. There we go. Now, think about I. Right here, I was very, very, very small. Now what's I going to be? Well, now I've got 100 volts peak at 0 degrees divided by 5,000, eventually 5,000, but I'll put 5,002 at 1.8 degrees because, you know, we got to see something. Okay, so 100 volts, that's 20 amps, or close to it, but I'm going to give it to you exactly. Divided by 5,002 gives me 19.9999. So here's what I'm going to say. I'm going to say I approximately equals, because, you know, 5,002, the difference between 5,002 and 5,000 is almost nothing. I'm going to say that that's going to be equal to 0.02 amps peak at an angle of 0 minus 1.8, so that would be minus 1.8 degrees, right? So that's my peak. Now, look at that. If we write I, this is 20 milliamps peak. 20 milliamps at minus 1.8 degrees, right? Now, 20 milliamps is a heck of a lot more than 6 milliamps, isn't it? So all of a sudden, we find that voltage drop across the thing. And in fact, we get hit twice by it because we don't get the extra whack we did here by squaring 28.6. We're not going to have anything like that here, are we? So the voltage drop that we're going to get is just going to be the point, I'll just write it this way, 0.02 amps peak at minus 1.8 degrees, which I have right above it, so you can see what I'm actually writing there, times R, and R is going to be 5,000 ohms at 0 degrees, right? So my voltage drop across the resistor, I'll just put delta V sub R there, is going to be 5,000 times 0.02. 5,000 times 0.02. I know, you're already there ahead of me, aren't you? Is 100 volts. So I'm going to put the little squiggly lines over there so that we can see. But really, this would have been 0.019999. But in actuality, this is what it is. So look at that. That's 100 volts peak, and I'll keep that, you know, minus 1.8 or whatever. So minus 1.8 degrees. If you really wanted to find out exactly what it was, let's just say that the drop there exactly, let me give it to you, 100 divided by 5,002 gives me that current times 5,000 gives me 99.96. So the voltage drop is 99.96 volts at an angle of minus 1.8 degrees. So it's literally the whole 100 volts is going to drop. Now, how do we understand that conceptually? When we look at the circuit that we have here, we can see that as I'm closer and closer to DC, I'm closer and closer to that thing where this starts as a short circuit and ends as an open circuit, right? I don't want you to understand it this way, but I'm just sort of telling you. So as we get over there, this is holding off at lower frequencies. This is holding off more voltage all the time. It's holding off more voltage all the time, low frequency. At high frequencies, the voltage is just flowing right through the capacitor, and this is going to 0, and that's why you get the 100 volts across it. All right. Okay. I think that I might hold it there. I want to also look at a CR circuit, but I'll do that in the next lecture. I don't have any room on this page anyway. So let me put this one up as sort of 7B, or I'll put it up as 8, but you know, and then we'll do another lecture on the CR. We don't have all that much left really to do. I've got to discuss decibels. I've got to discuss these filters here that we're getting to, because these are the applications of you understanding that. And I want to go through another slightly more complex circuit where we have both parallel and series components. I don't want it to be a mesh analysis circuit. I don't want to go that far, but I just want to show you guys one a little more detailed circuit where we've got both parallel and series capacitors, inductors, and resistors. Okay. All right, let me see if I can find out where I am here and I can actually turn you guys off.